Welcome everyone to this session on reinforcement learning, and now we're gonna learn how computers actually do learn, and perhaps also humans. We have seen the Markov decision processes, and those have a couple of components. They have states denoted by S, actions denoted by A, rewards denoted by R, and a transition model, a reward model, and discount factor between 0 and 1, the horizon that can be finite or infinite. And the goal here is to find the optimal policy pi star such that we actually maximize our discounted expected reward, so our total discounted expected rewards. And here you see that the transition model is basically the probability of going from one state to another, given that you have been in a state and have taken an action. And the reward model here is actually a stochastic reward model. So we have now the returns are stochastic. If we go back to the reinforcement feedback loop, we see that we have in the Markov decision processes an agent that takes an action and interacts with the environment. But we know actually so far by assumption what the transition probabilities are and what the reward probabilities are. Now, in more realistic cases, we don't know that. So we interact with the environment, and the environment only gives us a weak signal, so a reward. And we use that signal as a sample to learn from that sample. And that's reinforcement learning. Here it is. Now it starts. So we take the Markov decision process and we just relax the assumption that we don't know the transition model, and also that we relax the assumption that we know the reward model. So we don't know both of these models, and so one might ask, is this even possible to solve if we don't have these essential ingredients of the model? So you remember the Bellman equation, where we had the reward and we had the transition matrix. So it turns out that we will see some methods how to solve this, and that's the subject of these slides. Now, Markov decision processes, how do they work? Here we just find an optimal policy given a transition and reward model that we know, and then we execute the policy that we have found. In reinforcement learning, we learn an optimal policy by interacting with the environment, and the environment gives us a signal. So imagine you want to play a game of tic-tac-toe, or as people in the UK call it, noughts and crosses. You could actually open up a book like this one and read all the equations and write up all the equations to solve for the optimal strategy. But that's not what people do. Even children learn quickly what the optimal strategy is in that game by playing. And we're gonna see how actually reinforcement learning works by this fascinating example from the 1960s, before the widespread use of computers. Actually, Donald Michie invented a machine that is called the Machine Educable Noughts and Crosses Engine, for short MENUS. And that machine could learn to play tic-tac-toe, or noughts and crosses. And he actually used 304 matchboxes to do that learning. Machine educable, well, that's just machine learning from the 1960s. Here is the grid of noughts and crosses, and how this works is that you have matchboxes. So you find a matchbox with the empty grid on it, you give it a shake, there is a red bead coming out, and red is code for putting a circle here. So that's MENUS play, the computer plays here and puts here a circle, and all of those beads have different colors, and each color corresponds to a field here in this grid. Now, what do we do now? We don't want to lose against Menace, so we put our cross in the middle because that's usually a good place. So Menace turn is next. So Menace takes a look at the matchbox that has the same pattern. Well, it's rotated, but it's still the same pattern. We give it a shake. We get a blue bead here, and blue is code for putting a circle to the right. Now we can play again, and we put here an X. So, well, we're about to win against the computer. So let's see what Menace does. We take this matchbox that matches the grid or the environment that we have here. We give it a shake, and there is a green bead. And wow, that was a good move. So we haven't won yet, but we can make yet another move. So we put our cross here, and now you see Menace is not that experienced yet. We're gonna win, I'll tell you. So Menace takes the next move, looks at this matchbox with the same pattern. We give it a shake. We have a orange bead, and we put it there, but there is no hope for Menace. We have won in this game. And now it's the time where the reinforcement learning starts, because now Menace actually needs to learn from that bad signal. So all these moves were perhaps not the best ones. So we remove the orange bead, we remove the green bead, the blue and the red one. And that's how Menace learns. So if it loses a game, then we remove the bead from each box. In turn, when it wins, then we add 3 beads to each of the box for the winning move. And also draws are really good, because if you play perfectly, then draw is the best that you can get. And here we add 1 bead to each box to have a positive feedback. Now, this is showing how reinforcement learning works without having a model. The matchboxes do not have a sense of what a transition matrix is, but they still can win. Reinforcement learning agents use that too. So they might have a model. They might have the transition model or a reward model. They might have a policy, and they might have value functions. The value functions give the expected total rewards of the agent's policy. Now, it's gonna turn out to be really useful to introduce something called the quality function, which is basically the same thing as a value function, only that it also depends on actions and actions in the current state. So that's the expected total reward of taking a specific action in a given state. And that allows us to take different actions and then learn by trying out different actions. So we can rewrite our Bellman equation in the following way. So here you see the familiar Bellman equation, and if we define the V star of S as the maximum of the Q function, which depends on the state action pair, then we can just plug this in here, and we get here this Q function. And if we don't have the maximum yet here, we can write the optimal state state action value function as the Q star, depending on the state action pair, equaling to the expected return. So that's the return model basically, plus the discounted sum of the expected future rewards. So that's our transition model that we have here. And so this is now with the knowledge of the model, but we want to actually learn these two parts of the Q function. So to do that, there are a couple of different types of reinforcement learning agents. So from the perspective of the ingredients, we can have a value-based reinforcement learning agent, and that's a little bit weird because those value-based reinforcement learning agents, they have a value function but no policy function, at least not explicitly. Yeah. Why is this weird? Because actually the goal is to maximize the expected future reward, to find the optimal policy that maximizes those. So on the other hand, there are policy-based reinforcement learning agents. They don't have a value function, and this is also weird because how can we improve our policy if we don't know what the value of it is? So there are also actor critique reinforcement learning agents, and they have a policy function. They try to improve the policy, and then they have a value function that critiques the action that the actor has taken or the agent has taken. From a different perspective, we can think about reinforcement learning agents, whether they are model-based. That means, well, if we don't know the transition model and the reward model, well, we can learn via samples about them, we can estimate them and plug them in. But much more popular are model-free reinforcement agents that do not actually put any interest in the specific form of the transition functions or the reward functions, but they just want to find the optimal policy. So those are the most popular. Then there is a middle ground, which is imitation learning. Here we don't have a transition model and also no reward model, but we get some expert signals about the reward. A couple of ways to actually reduce the complexity of the problem are shown here, where we first take a look at dynamic programming backup, which is the usual value function, value iteration actually that we have seen before. So this is basically going through all the branches and checking out what is the value. Then we get an estimate of the value of each of the states. Now, to simplify this, we can also do a Monte Carlo backup where we only go through those episodes that we actually use and use them to estimate the value of our states. A third one, which is even shorter here, is the temporal difference backup, which goes from one state to another state. So it has a state, action, reward, future state quadruple, and this is a way to learn as well. And we will see all of these methods later. Now, to understand a little bit better how reinforcement learning agents can work, let's take a look at this toy maze example, also known as Grid World. And here we have two terminal states. One is the +1, that's where we want to go. And one is -1, which we want to avoid. We start in 1-1, in state 1-1. And here we have already some labels on those states. So some basically not labels, but actually names of actions that we want to do. So a policy is here on this grid. So the policy is up, up, right, 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 and then we end up in +1, hopefully. But if we go from 1-1 and slip to this place here, and slipping might happen easily in these kind of environments. Imagine you have a little robot that gets stuck on the carpet with one wheel, and the other one is on the ground, and the one wheel is spinning, and then it turns around, and then it goes to a different direction than it intended. Exactly that can happen here. So that's the transition probabilities. That's also called noise. And this makes us slip sometimes. And in each step here that is non-terminal, that is not one of these end states, we have to pay a cost for moving or for burning energy, for consuming some energy here. Yeah, and so the question is, what is the value of being in each of the states? So to illustrate actually this grid world, let's take a look at that, how this could look like in this example. And we have here exactly the grid world that we have seen on the slides. And here I can go up, up, right, 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 and I got it. And another time, oops. There we go. I go. And I got it again. So if you play this a couple of times, I got lucky now, then you will see that you sometimes slip and you fall into actually the bad space here, the bad state here. So now, what are the optimal values? You see here actually exactly that grid world solved for the optimal values with value iteration. So here's no learning, and we got 20% noise, so that's the slipping. And here you see also these arrows, they say up, up, right, 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 and then you get it. Yeah? And this is what we want to learn now with learning and not with value iteration where we know the model. Here are some references and some takeaways. So by 3 methods is it that we learn some wisdom. First is by reflection, and that's model-based reinforcement learning. Second, by imitation, and that's imitation learning. And third, by experience, which is model-free learning. And we got a couple of reinforcement learning agents. Some are value-based, some are policy-based, some have both value and policy-based components. Some are model-free, and some are model-based, and imitation learning is a middle ground. Thanks for watching.